Right. Section 9.4 deals with a concept called the cross product. Now, a cross product, okay, unlike a dot product, a dot product of two vectors is equal to a scalar. But the cross product of two vectors is a vector. And we'll introduce the situation by looking how it arises in physics and engineering. Again, you don't need to have taken a physics class, but let me just, you know, I like to motivate where these things come from. That's part of the course. So here, how many of you have heard of the concept of torque? Concept of torque. Okay. Okay, definitely some of you have. Excellent. Excellent. So if you tighten a bolt, by applying a force to a wrench, as I show here in figure 1, we produce a turning effect called torque. Okay, and here's the little picture here. You have a bolt and you have a wrench, and you're applying a force. You're holding the wrench and you're applying the force, not necessarily perpendicular to the wrench, but at the force that they're showing there. And when you apply the force in that direction, the wrench is going to move clockwise. So when the wrench moves clockwise, are we tightening the bolt or loosening the bolt? If you think to, you know, maybe if you tighten the bolt on a bicycle, or you know, put a molly bolt in a wall, it tightens. That's right. That's right, Mario. It tightens. And so the bolt, like if we're tightening a bolt, let's say this is a bolt that we're tightening into a wall, like how many have used a molly bolt, maybe to hang up a whiteboard or something like that, to hang something up on a wall, like a molly bolt or a bolt. When you tighten, the bolt goes into the wall. So the direction of the torque is into the wall. And that's what that cap of T is, the torque vector, and it goes it goes in there. Think about the wall there. The bolt gets tightened and it moves into the wall, and that's the direction of your torque. Now, what affects torque? Okay, would a bigger wrench produce greater torque? If the wrench is given by that vector R. It's denoted by vector R. So vector R runs along the length of the wrench. You know, the wrench has a length, right? That's the magnitude of the vector R, the length of the vector R. Would torque be increased or decreased if the wrench were longer?
Increased.
It would be increased, absolutely. And I'm sure you've seen mechanics mechanics have different sizes of wrenches. So if you're trying to really tighten a bolt, pick a wrench with a longer handle. But also applying more force also increases the torque. Okay, so this is really what torque's about. Now, is the force that they're showing there, is all of that force being used in producing the torque in figure 1? Is all of the force that you see there, the force vector, is the entire force vector being used in producing torque? Or is it just a component of the vector force?
It's a component along with sine.
That's right. That's right, Mario, because it's the vertical component of that vector that is producing the torque. Because what causes the wrench to turn? It's the vertical component of the force that is causing the wrench to turn. Right? And so this means then, if we go a little further down here, okay, in the picture, okay, there's the wrench in figure 2, and there's the force vector in figure 2, and the you have an angle between the wrench and the force vector, and by alternate interior angles, that theta is also down there in the bottom of the triangle, and clearly the sine of theta is equal to the opposite side over the length of the force vector, and so the opposite side, the y side, in that right triangle is equal to the length of the force vector times the sine of theta. Okay, let's make sure everybody sees it okay. I want to make sure that you see it all right. Are there any questions on that? All right. Well, then the magnitude of the torque vector is equal then to the product of the length of the wrench vector, the magnitude of your force vector, and the sine of the angle between the two. Okay, that's your torque, the magnitude of your torque. And if you want then the actual torque vector, the torque vector, let me just, I don't want to highlight everything here. The torque vector, let me just, okay, the torque vector then, remember the torque vector is a vector. So it would be the magnitude of the torque times the normal vector that goes into the wall. Okay, and you can actually determine what direction the normal vector is using what's called the right-hand rule. So the torque vector that you see, and we'll get there in a moment, but the torque vector that you see here, it is defined as what's called a cross product of the vectors, the vector r, the wrench vector, and the force vector f. That's called a cross product of two vectors, and this is where a cross product comes from. So if we go down a little bit, they say that this type of expression, okay, occurs so frequently in the study of fluid flow, planetary motion, and other areas of physics and engineering that we define and study the cross product of any pair of three-dimensional vectors A and B. So this is a very widely used concept, very widely used. So definition here is that, hold on one moment. Let me see, let me get that up a little bit more, class. Yeah, if A and B are non-zero three-dimensional vectors, the cross product of A and B is given by this vector that you see here. Okay, it's the vector points in the direction of the normal vector n, and the scalar multiple of that vector n is the length of A times the length of B times the sine of the angle between them. And the normal vector, again, it's a vector perpendicular. Well, if you think about the example with the wrench, if I go back for a minute, it's a great example. Here's the figure 1. There's the wrench and the force vector. The wrench, think of the wrench vector r and the force vector f. Think of those two vectors as being in a plane. Well, the normal vector n is perpendicular to the plane that contains the vectors r and f. And in fact, the cross product of two vectors is always perpendicular to the plane that contains those two vectors. Okay, it's a natural thing for the torque vector to be perpendicular to the wrench and the force vector, those two vectors. It's a natural thing. You know, if you turn the bolt, if you apply too much force, the bolt's going to go through the wall, right? Because that's the direction of the torque. So it makes kind of natural sense in terms of that application. And then formally, in figure 3, they talk about the right-hand rule giving the direction of the cross-product vector. Okay, so if you, how many have heard of the right-hand rule? Maybe you've seen that in another class. Okay, okay. Charles, Ellie, and Gordon have seen it, and Kino, and so what's going on here is if you look at the vectors A and B, they're in a plane, right? They're in a plane, and there's the angle theta that goes from A to B, and if you take your, like they show the right hand there, if you curl your fingers, okay, in the direction from A to B, your thumb points upward. Your thumb points upward, and so the cross product of A and B, A cross B, is going to be in the vertical direction. Okay, does that make sense? A cross B is in the vertical direction, and it's in the direction of the thumb, and that vector A cross B is perpendicular to the plane that contains the vectors A and B. All right, so we say then that, hold on, if I go down a little bit here, that the vector A cross B is orthogonal to both vectors A and B. Okay, so let's look at a few examples. So really I'm giving you a guided tour here of this section. In example one, a bolt is tightened by applying a 40 Newton force to a 0.25 meter wrench, as shown in figure 4. Find the magnitude of the torque about the center of the bolt. Okay, well, the magnitude, so we use the definition of the cross product. We use the definition of the cross product here. Okay, one moment. Yeah, try to do it that way. So here, the magnitude of the torque is equal to the magnitude of the cross product of the wrench and force vector, and you're going to get 9.66 Newton meters. All right, are there any questions on that? All right, very good. Well, let's go look at some more examples here. One moment. So here, they want you to find I cross J in example 2 and J cross I. Now, these are very standard basis vectors, I, J, and K in 3 dimensions. Okay, and you don't really need to use the formula. I mean, here, they show you how to use the formula right here. If you wanted to use the formula to find the cross product, you could do that. It's the K vector. But it's a little easier to use the right-hand rule. If you take your right hand and curl your fingers I to J, curl your fingers on your right hand from I to J, what direction does your thumb point? Try it and see. Figure 5. Curl your fingers from I to J, your thumb points up. So I cross J is equal to the K vector. Good. Now, what if you did J cross I? What if you take your right hand and you curl your fingers from J to I? What direction does your thumb point? Points downward. That's good, Ellie. And so J cross I equals the negative K vector. Yeah, Mario, I'll just stick with my right hand on that. So, I mean, are there any questions on this? Okay. Okay. Well, if there are no questions, let's move on. So, one thing we can speculate is that B cross A equals negative A cross B. We just saw that with the example we did. I cross J is equal to negative J cross I. And that in fact, that's not an accident. That's a property of cross products. So down here, they have here just some properties of the cross product.
Hey, Professor.
Yeah.
I don't know how to do the right hand rule with like whenever it's J times I.
Okay, hang on. Let me see if I can, one moment. Okay, so I'm going to take my right hand here. Let's see. Now, J times I, J is on the y-axis, right? And I is on the x-axis.
Yeah.
So J times I, are you able to see me okay on my video? You're able to see my hand? Okay, J cross I. Well, if I curl my fingers like this, I'm doing I cross J. So I have to flip my hand. And you see here, it's like I'm moving the y-axis into the x-axis. J cross I, and my thumb points downward.
Okay, so that means that whenever you have your hand upside down, that means the axes are switched. The y and the x axes are switched.
Well, they have to be. But let me ask you this. What would hold on here. Let's try something. One moment. What would I cross K equal? Okay, so I cross K. One moment. Let me. Okay, one moment. Sorry. One moment. I don't want to read email now. This is class time. So I cross K. Hold on, I'm going to take my video off. One moment. Okay. Okay, so I cross K, if you, maybe I can draw a quick picture here. Okay, there's I. Sorry. Get over here. Man, hold on now. All right. Here's I, here's K. Okay, so I cross K, you got to hold your, man. Yeah, you got to hold your hand kind of like this. What would I cross K be? If you're doing I cross K, yeah, it would be negative J. That's right. It's like you're doing, it's like your thumb has to point to the left because you're bringing the I vector into the K vector. So I cross K equals negative J. What about K cross J? What about K cross J? Here's J. What would K cross J be? Let's see. Ellie says it's I. K cross J. This is J. Hold on. I can draw that a lot better than that. Come on. Yeah, I was thinking negative I. That's right. Because rotate K into J, and it's like you have to do this. You have to do this. I hope this is working for you all. You get negative I. All right, was this helpful? Does this make good sense? Are there any questions on that?
Yeah, so for the right hand rule, whenever you do J times I though,
J cross I.
J cross I, you have to not just, hold on, let me just show my video. I think that like, so regularly from like I cross J is like this irregular.
That's correct. That's correct.
But whenever you do J cross I, instead of going like this, because that still means that you're doing I cross J, but instead.
No, that's J. No. The first one, do your thumb up. That's I cross J.
Right.
But now flip your hand. That's J cross I.
It's still you're still bringing.
Vector.
I think that it's actually that you have to move your hand this, like you have to move it this way in order for you to do J to I when you curl
That's
your
correct.
hand.
That's correct. And your thumb's pointing downward.
Right.
That's right.
But it's just, but like I'm just saying that like doing it like this way, like I don't know, it's like my hand is in this direction, that's why you're curling it from J to I, but like by having it like this is just like still going from I to J. So
No, it's going J to I. It's going J to I. It's going J to I.
Oh, well, all right.
It is. Your question's a good one. I don't know. Would anybody like to show their video and maybe show their perspective? Share their video, I should say. Any other students? Ellie says you have to do it so that your finger palm is. Yeah. So that's a good point. So your fingers, if you're doing like I cross J, your fingers are. Yeah. What we'll do, we'll practice a little. We'll practice a little after class. Don't worry. Don't worry. I think just give it a little time. Give it a little time. You're going to get this, okay? You're going to be fine, okay? All right, you're going to be
All
fine.
right,
You're
thank
going to be
you.
fine. Sure, no problem. Maybe what we can do is during the next break, uh, we can we'll practice a little. Okay, don't worry, don't worry. And then yeah, and I see some chats there. I see some chats. Let me just I mean J cross I would be this. So think of it like this. My fingers are bringing the y-axis into the x-axis. My fingers are bringing the y-axis into the x-axis. And so that's J cross I, and my thumb points downward. And so it has to be J cross I equals negative K. It's a little harder to do with the other combinations, but you know we'll work on it. Don't worry. And anybody that's having a little uncomfortable, we'll work on it. Okay, don't worry. You see me after, like before, right after I'm done here, and we'll work on it. Okay. So now what we have here is our properties of the cross product. These are just properties. Okay, they're sort of natural, these properties. The first one we already believe in. The second property, if you have a constant times a vector, and you cross product that, like constant times vector A with, and you cross it with B, the constant can be pulled out in front of the cross product. The constant doesn't change the direction at all. The constant doesn't change the direction. Now it will change the magnitude of your cross product vector, or the length of your cross product vector, but it won't change the direction of it. And then you have a couple other rules here that are kind of natural, and I'm just gonna, I'm gonna move on from there. If we move on here, now something else that's important that we'll need to use later on when we get to surface area is if you have the area of a parallelogram, that is actually, you can find the area of a parallelogram if the parallelogram is bordered on the sides by a vector A and a vector B. The area of the parallelogram is equal to the length of the cross product AB. And the way you can sort of think about it is, they have a picture there. Let me just see. Maybe I'll go to the whiteboard on this. One moment. Let's see. So hold on. I'll try to draw it. Okay, there's a vector A. Here's a vector B. And we can complete the parallelogram like that. This is A. This is B. Now, let me ask you this. If I were to take this rectangle, I want to say this the right way, and fill it in over here, are those two rectangles the same?
In area, yes.
Yeah, they are. The two rectangles have the same area. So the area of the parallelogram includes this rectangle. Okay, and it includes this space here. Okay, but if we were to take away this triangle and put it over here, the area that we have here would be the same as the area of the parallelogram, right? In other words, I got it. Hold on, I'll do this a little better. One moment. Let's try it again. Okay, I'm going to draw the parallelogram. Okay, one moment here. Okay, that with vectors A and B. And then below, I'm going to draw good, excellent. Okay. Now, do these two, we have a parallelogram here on the top, whose sides are vectors A and B. And then we have a rectangle at the bottom. Okay, we have a rectangle at the bottom. Do these two, and maybe, I don't know, maybe I can make it a little longer. Takes time to do things perfectly, but sometimes it's worth doing. Well, it's always worth doing to do your best, right? I don't want to be sloppy, you know. Okay, so does it look like these two figures, the parallelogram and the box, have the same area? The parallelogram and the rectangle?
Only after cutting the triangle of the parallelogram onto the other side, I could see that, yeah.
Good. That's what I want. See here? Okay, so if you were to, yeah, they're the same. So the point is that if this is angle theta here, this is angle theta, then this side here, hold on, wait a minute, I got to have this as B, and I got to have this as A. Okay. That's the way the book has it. So this height here is going to be the length of B times the sine of theta. Okay, and that's the same, by the way, as the height for the rectangle below. It equals the length of B times the sine of theta. Now, what's this length here equal to? What's this length equal to?
The magnitude of A, vector A?
That's right. And so the area of the rectangle, the area is equal to the length of A base times height. The height is the magnitude of B times the sine of theta. We all agree that this is right, and we can see that the area of the parallelogram, basically the area in the parallelogram can be moved so that the area is preserved. The parallelogram can be altered to be this rectangle, and the rectangle has the same area as the parallelogram. And that's why the area of the parallelogram is, this is the formula for that. All right, are there any questions on that? It's like cutting out this piece of the parallelogram and moving it over here. It's exactly what that is. And then you get a rectangle, and we know how to get the area of the rectangle. This is the area of the rectangle, so that's equivalent to the area of the parallelogram. Okay, who's feeling good about that? Who's feeling okay? Maybe give me a thumbs up if you're comfortable. Okay, excellent, excellent. Okay, very good. Are there any questions? Okay, good. Well, then let's go back to the book. Okay, back to the book. Giving a guided tour here. Okay. Okay, this is a very important concept. How the magnitude or the length of the cross product vector is equal to the area of a parallelogram whose sides are formed by vectors A and B. That's a very important concept that we're going to be using later on as well. All right, so let's go a little further here. Now, the formula for the cross product that we have is nice, but the problem is if you have two vectors, you don't always know the angle between the two vectors. Okay, you don't always know the angle between the vectors. And then what are you going to do? Okay, well, you know, I know there's stuff you can do, but it would be, suppose we always know the components of the vectors. So what if we could compute the cross product with a formula based on the component forms of the vectors? Well, there is a formula, and they derive it by, they take the cross product of A and B, and using those properties that are on the previous page, they come up with a formula for the cross product vector for the components. Okay, and we don't, I mean, you can look at that. We basically then, I mean, this is, if you want formulas to find the components of your cross product vector, these are the formulas. The first component is A2B3 minus A3B2. The second component is A3B1 minus A1B3. The third component is A1B2 minus A2B1. Okay, so this is, but the problem is it's difficult to remember this formula. Okay, it's difficult to remember that formula. All right, so, you know, if, you know, you're not allowed notes, for instance, on an exam, how are you going to remember this formula? Okay, there's a better way to get the cross product. Better way to get the cross product. But we have to talk about determinants to do it. So a determinant, if you have a 2x2 matrix here, A, B, C, D, the cross product, or the determinant, which we use vertical lines to denote determinant is equal to AD minus BC. Okay, how many have seen that for determinant? They give an example below where they compute a determinant. Okay, good. That's something that most of you hopefully have seen. And okay, no problem. Well, you know, why is this helpful? Why is this helpful? Well, turns out that if we consider a determinant of order 3, okay, then this is gonna allow us to get that complicated formula. Here's a 3 by 3 matrix, and the determinant of order 3 is defined this way. It's defined this way. Now let me show you how they get this, just so you know. I mean, that might be hard to remember too, right? So let me just well, let's see here. Look, I want to say this right.
Are you asking about how to solve this matrix?
Well, I'm debating. I want to do a cross product between two vectors. I want to do an example, and I want to show you why using this approach will work. I'll tell you what. Let me go right to the whiteboard here. Let me go right to the whiteboard and do an example right here. Okay. Okay. Let me do one right here with you. Sometimes it's better just to, and the example I'm doing is actually going to be example 2 from the textbook. So I'm going to have a vector A, which has components 1, 3, and 4. And I'm going to have a vector B that has components 2, 7, and -5. Okay? And I want to do A cross B. I want to find the cross product of the two vectors. Okay? Now here's what you do. Here's what you do. You set up a 3 by 3 matrix. 3 rows, 3 columns. And the first row has an IJK on it. The second row has the components of A, 1, 3, 4. And the third row has the components of B, 2, 7, -5. Okay, so what we're going to do is we're going to compute a 3 by 3 determinant using the formula, essentially, that I just showed you. But of course, it's not an actual determinant, because an actual determinant, you have to have numbers. It's all numbers. This is just a way to help you find a cross product without having to remember that kind of ugly formula. Okay? So what you do is this. Okay, so the vector I, if you look at the vector I, think of it though like an element of a matrix. Okay, the vector I is in the first column and the first row. So what I do is I say, okay, well, there's a submatrix right here that has 3, 4, 7, -5. I'm going to write the determinant of that submatrix right here, 3, 4, 7, -5. Okay. And I'm going to put an I right here. Okay. All right. Now, there are three parts to this. Let me write down that matrix again. Okay, now the next part, remember what we're going to be getting here. We're going to be getting a vector. We're going to be getting a vector. And the next part, well, we're in three-dimensional space, so we need an I, J, and K, right? We have a minus. We always put a minus there. And then we got to have some 2 by 2 determinant times the vector J. How do we get what's in there? What the 2 by 2 determinant is? Well, what we do is we say, okay, here's J. J is in the second column and the first row. And so what I'm going to put in there are the 1, 2, and the 4, negative 5. 1, 2, 1, 2, and then 4, negative 5. Finally, we have a plus. So it's always the first, this is always a plus, this is always a minus, this is always a plus in front of there. That doesn't change. Okay. This is a little like cofactor expansion if you've taken linear algebra. Cofactor expansion along the first row. Here we have a vector k, and now we have to fill in the 4 numbers. Can you tell me what the 4 numbers are going to be?
1, 3, 2, 7.
That's right. Good. 1, 3, 2, 7. Because that would be blocking out the entire first row and the entire third column. And then that would give you 1, 3, 2, 7.
So you have to say it from left to right then? And then from top to bottom when you say
you go from left to right and you do it exactly like this every time.
All right.
Every time. So this isn't like linear algebra, Math 284. You can do different cofactor expansions and get the same answer. You don't do that here. You do it just like this. Okay. And now we're going to find out what the vector is. So of course, we got to compute the determinant. So this determinant, well, that's 3 times negative 5 minus 7 times 4 times I minus, okay, the next determinant is going to be 1 times negative 5 minus 2 times 4 times J. And then the last determinant is 1 times 7 minus 2 times 3 times K. And so what we'll get here is, looks like negative 43I. Let's see, minus, well, this here is equal to negative 13, right? And a negative times a negative is a positive, so that's a plus 13J. Okay, and this here is just what? That's 1, right? So you get plus a 1K. This here, of course, was negative 43. And that's your answer. That's how you compute the cross product. So like for the exam next week, in your work that you'll submit, okay, and I might just have you upload it in WebAssign while you're taking the exam, you know, and that way it's convenient and it's like live. this is the kind of work I would want to see for a cross product. Okay. And you'll be definitely computing some cross product vectors, but that's how you do a cross product. Are there any questions? Any questions at all? Okay.
Professor, I got one question.
Yeah. Yes.
The examples that you show in class,
Yeah.
other than this one that you freely wrote, like just like the ones that you show in text, are those also like concepts that are shared on WebAssign on our WebAssign homework as well?
Well,
I'm just asking because I didn't copy down the examples this class, but I know that I can always refer back to the video recording if I wanted to, but I just wanted to ask.
I think it's good to always copy examples down that I write, whether it's on the board, like the whiteboard, or you know, but you know, I think the majority of students do copy. You know, like even like this example is a good one to copy down too. But yeah, I mean everything's hopefully helpful, and but like you say, it's in the recording. So if there's something that you feel you want to copy down later and put in your notes, that's okay. It'll be in the recording.
Okay.
This is why I like recordings too, as opposed to like having, you know, files, because recordings I include stuff like this. Recordings are recordings are like, you know, they include everything we do. And I sleep better knowing that you have everything. Good question. Good question. Are there any other good questions? Okay, I'll stop the recording.